and we worked together on this, what we call evidence passing semantics. So we first described this evidence passing semantics in this SFP 2020 paper. And the key idea of evidence passing semantics is that instead of searching handlers when operation is performed, why don't we push down the handlers during program evaluation? So now, when operation is performed, it can very quickly look at what we call evidence, but it's basically a list of handlers that gets passed down at runtime. You can look at this evidence and immediately find, sometimes based on the types, that where the handler is that is going to handle your operation. And also, if the handler happen to be a tail resumptive, which means it will resume in a tail position. To think about tail calls, but we call this tail resumption because it resumes in a tail position. If that's the case, then you don't even need to jump to where the handler is defined and capture the continuation. Instead, you can just evaluate this operation in place. So no more capturing and very easy searching. And we show that a lot of operations, they are actually tail resumptive, like rigorous or like very efficient implementation of stateful resources based on in-place updating, for example. They will all be tail resumptive because you can change the thing in place. And we provided a Haskell library as well that's used to implement this evidence passing semantics. But the semantics in the SFP paper and then later the Haskell paper, they all come with one restriction that we call scoped resumption. So that basically means whenever you capture a continuation, the continuation can only be resumed under the exact evaluation context. Not the evaluation context, but it has to be resumed under exactly the same set of handlers that are available in the evaluation context. And that's basically why you can statically tell very efficiently which handler is going to handle it, because you will not be able to change the handler for the continuation. But there are some programs that you cannot write with such a restriction. So we later lifted the restriction in a follow-up paper at SFP 2021, and now the semantic is slightly more dynamic than the previous version, but it has the full expressiveness of effect handlers. And we actually did a little bit of benchmark to show that the semantics in SFP 2020 paper will actually be more efficient. But it's basically a trade-off if you want full efficiency or you want the full expressiveness power. And it also turns out that this evidence passing semantics can be directly used to implement that named handlers that we discussed yesterday. So basically we give handlers, each handler a name, so whenever you perform, yes?
Oh, sorry, what was the, maybe you'll talk about it later, but what was the issue with the, between the second and the third paper again? Like what was the expressive restriction?
Yes, there is a restriction on the expressiveness. And the restriction is whenever you capture a continuation and you want to resume it, the continuation has to be resumed under an evaluation context that has the same set of handlers as when you captured it. So when you captured this continuation, you captured it under an evaluation context, right? And the evaluation context might have handler A and B. And when you resume this continuation, your evaluation context must have handler A and B as well, no more and no less. Okay. And that's restrictive because there are functions you cannot write with this restriction.
Okay, thank you.
So named handlers are also an existing feature in Coca, and it comes with lots of examples to demonstrate that you can use named handlers to write effect handler programs more flexibly, because now you know exactly which handler is going to handle this operation. And there are still active studies on how to implement effect handlers. Like for example, WebAssembly people So they proposed a primitive basically to implement continuations in WebAssembly and then use that primitive to implement effect handlers. But in one way or another, you either have a very specialized runtime support for efficiency, or you can encode it in a different way, like CPS transformation, that allows you to not touch the target runtime, but it will be less efficient than if you have special runtime support. And there is this effect handlers benchmark suite that people use to compare across languages. So it's, there is this GitHub link there. So they implemented the same program using different languages and compare their efficiency. And you can see that efficiency can vary a lot across languages and across programs as well. So what have we talked about in this lecture series? We talked about algebraic operations and algebraic effects, and we talked about effect handlers, and we talked about effect type systems and how you can ensure syntactic type safety once you have effect type system. And we talked about different implementation techniques that people use to implement effect handlers in different languages. And here is a list of resources if you are interested in effect handlers. So there is an effect bibliography that Jeremy Yellop at Cambridge has been maintained. So it basically has a very, very long list of papers and softwares that are related to effect handlers. So you can find all these related papers and effect handlers from that GitHub. And of course, contributions are welcome. Matija Pritina has this tutorial paper, An Introduction to Algebraic Effects and Handlers, in 2015. So that's a very nice tutorial paper. That's basically the first paper I read on effect handlers. So it comes with the syntax, operational semantics, and type systems, and a lot of examples as well. So if you are interested, you should definitely check it out. And as I said last time, I think Sam Lindley has a version of effect handlers here at OPLSS in 2022, and he talked a lot about links. And there are lots of examples that you can write in links for effect handler programs. Dan Leyen and myself gave a tutorial at SUP 2021 specifically about Coca. So there are examples for effect handlers, how to write effect handler programs in Coca, and there is also this special reference counting technique we use in Coca that's actually also implemented in Ling, that's called Perseus, and we show how you can write very functional but in place programs in Coca. That just means the program is functional, but under the hood it will do in place updating. And lastly, Andrew Bauer has this lecture on what's algebraic about algebraic effects and handlers, and there is also this lecture notes. So if you are interested in the categorical foundation of algebraic effects, you should definitely check it out. I think he also gave the lecture at OPLSS a few years ago before Sam Lindley. So it focused more on the categorical foundation of algebraic effects. So that's all the slides I have. They have some references. And in the rest of the time, we will do some programming. Because we talked about the semantics foundation for algebraic effects. We talked about the operational semantics for effect handlers. We talked about the types. But the thing that we haven't done yet is programming. So let me change the setting. Is this large enough? Okay, so I think that the easiest way to implement effect handlers library is by using free monads in Haskell. You may or may not agree with that. But if you have Haskell installed on your laptop, let's try to go through this together. So, what do I have? Okay, the first thing is free monads. Because we are implementing effect handlers based on free monads, we need to have a definition of free monads. And this free monads definition is the same as we have seen on the lecture slides. It's just I put a can annotation for F to explicitly tell you F is actually a type constructor that goes from type to type. How many of you have heard free monads before? Cool, that's more than I expected. So there are two branches, right? The two branches basically says a program in free monad is either pure, and in that case it carries a value of type A, or it is an operation, right? Think about that computational tree we have seen before. It is the operation that is operation specific to F, and F has a lot of children, right, in that computational tree. That is again this free monad. And the first thing we are going to do is we are going to define the monad instance for this free data type. So that means we need return and bind. And what would you do in the return? Pure. Yes. Because you actually have a value now, which is x, right? And there is nothing, there is no computation at all. You would just wrap this x in pure. Right now you have actually a value of this type A. And we still need to define the bind operator. And here we have the signature for bind just in the comment. Now, can you tell me what we should do for the bind in the pure case? If you look at this type signature, what things can you actually do? GX. Exactly, GX, right? There is nothing else you can do. You have an X available, you have a G available, you want to return something that has the result type B. Like what choices do you have? You can only apply G to X. And one nice thing about Haskell is once it type checks, it's basically right. And how about OP? Yes?
Maybe you pass the G further in?
I pass the G further in. Yes, but how could I do that? So the type of Y would be something like this. And if we want to pass the G further in, then we need to know something about F. Right? There needs to be something about F that we need to know. Otherwise, really, there's nothing you can do at this moment. And if you think about computational tree, right? You have a tree whose internal nodes are operations, whose leaves are values. Then you want to apply G to all those leaves, right? This is what this binder is basically doing. Then you have to be able to pass this G down to this in the tree. Yes.
Do you have to call the binder somehow on the children?
It's very similar to that. So, because F is the internal nodes at this moment in that computational tree, and we want to apply G to all its children, then basically what we need is for F to be a functor. I'm going to add functor F. Oops. And once you have this functor, you have available the function f map, right? And now what you can do here, you still need something of the g, but you can actually now at least map g to map g to y, right? And what would that give you? That would give you free, what will give you f, but then free of that b. So you still need to wrap this whole thing to an O. And this is still not quite right yet, because as you are pushing down this g, you don't want just the g, because g is something that has to be bound. Right? So it actually needs to you actually push down the bind of g. So if you want to think about it intuitively, it's basically we are pushing down this function g down to every leaf of your computational tree, so that we can actually apply g to this x. Yes?
Is this tree always just a straight line, or does it somehow branch? Because I don't understand how it could branch, but I think that's just a beginning.
How it could branch depends on how you instantiate data with f. So because, for example, if f is put, then you can, or get, you can actually imagine you will have two children. Right? If it's a put, then you only have one children. But in any case, you want this whole thing to be something that is mappable. You want all the children to be mapped to this point. So there are lots of resources that you can find online about free monad. So in this case, as long as this f is a functor, we get a monad instance definition for free f. And of course, we need applicative and functor. Defines them based on the monads, but this is not very important. Basically, once you got this monad instance, you can also define applicative and functor based on that. And now we have this free monad. We can already start defining effects. And what would effects be in such a program? Well, it will just be a data type. So let's think about exception. So exception is something that has a single operations row, right? And in this case, it does have just one data constructors row. But in the data type, you also need to keep track of the return type of your continuation. So basically what sometimes people call the answer type of your continuation. And if you think about the signature of throw, right, it basically says throw takes the unit and returns you arbitrary A. And in this case, we just omitted that unit. But this corresponds exactly to throw takes the unit and gives you back an A, roughly. And the most important thing that connects the effect we are defining and the free monads is we instantiate that f in that free monad. Because, again, if you look at the definition of the free monad, here is the case where you have a value, where you have this leaf of the tree, and op is the case where we have to give it the operation of the internal node, right? In this case, this f. So if we instantiate this f with this exception, then actually what we get is, let me copy over. So once this f is instantiated with exception, then you actually get these two cases, right? So you got a tree in this case where the leaves are the pure again, but the internal nodes in the tree, they are these exceptions. In this case, the exceptions, if it has children, then it's going to have this type. That is like another tree that you can have more exceptions further down because exception is the current effect that is allowed in this program. And here, this throw is just a convenient function we use to embed this throw in this operation. So we can always use this throw instead of this off throw. Now with that exception defined, we can already start writing functions, right, without writing handlers. So imagine that we are going to define a function that there's safety, so it does division, m divided by m, but it raises an exception when m is 0. So how would you implement safety? Yes?
Pattern match on n, like case n is 0.
Then
Throw.
0 else. Right? Like now you have a case branch on the value of n, and if it's 0, we will throw an exception, and if it's not, we will do the real job. And you can actually see that, well, once we have this wrapper created correctly, you don't really need to know what this phrase is doing, but you can still intuitively write this definition of safety. Right? Once we have this definition, we haven't figured out how to handle this operation, right? Yes?
What happens if you call that, like, in the current implementation, if you call it without a handler? Will it get stuck, or will it be a weird?
It will give you back a data type,
Okay.
a value of this data type.
Okay.
Yeah. But basically, it's an effective program that does not run yet. But having the effective program is not enough, right? Because we don't know yet how to handle them. So let's try to write a handler for this throw operation for effect for this exception. And here I get the type of this handler. So what does this handler want? The handler says, I'm going to take a program of this type, and you may throw exception in this program. But I'm going to handle that exception, and I'm going to return something of type maybe A. So now, how would you implement this program? Let me also copy the type of real again. Mm-hmm. Yes?
So what I would do is introduce a variable, and then case analyze the variable.
Analyze that variable, yes. And what cases will have?
It's either pure or an off.
Exactly, right? Because you know the input is a data type like this. And you know there are only two cases of this data type. So you only need to worry about two cases. Either it is pure or it is an off. And what would you do in the case of pure?
Return just X.
Because we know the type of this whole program is a maybe now. If the computation has successfully returned a value, then you just need to wrap it in a just, and then you got maybe A. And what happens in the case of an operation?
Nothing.
Nothing. Nothing happened.
Just -1.
Okay, now we have successfully implemented our first handler for exceptions, and we can try to run it. So we can try to run it by handle this program using this handler, and we can do 42 divided by 2. Oh, oops. No instance for show. What? We're not returning the free. We are. Oh, maybe I'm about to reload it. Oh no.
Looks like maybe it's wrap texting.
The maybe is wrapped accidentally.
Like wrapped in the free. Also, it's a show free maybe.
Oh, I see. Okay, because I have 3 files here. So it's loading from a different file. Cool. Now this is a successful division, right? But you could also have unsuccessful division if you try to divide 42 by 0, and in that case you will just get nothing. And that's exception, so we can move on to slightly more complicated effects. For example, state. And in the case of state, we have 2 operations, right? We have a get and a put. And in this case, this state has 2 types, S and A. And S is the type of the state, and A is again the type of the return type of continuation, like in the case of exception. So if we want to map it to what we have in the previous lecture, then this is basically saying get is something that takes a unit, but we ignore this unit because the unit doesn't give you any information. And put is an operation that takes S and then a function that takes a unit and give you back an A. But again, we omitted this unit, but we could put it there. It's not that interesting. And this is a more concise way to write it. Now we have actually distinguished between values and effect for computations. Okay, I think I will just give you the definition of functor, because as we said that you need that f to be a functor in order for that free to be a monad. But in this case, let's just so this would be the definition of f map for state. So basically, you try to push that f to that continuation in both cases. But that's fine. Now, what's more interesting is that, like in the case of exception, let's implement some wrapper functions for get and put because it's more convenient to use. And you can consider this basically as a way to write like a generic effect based on algebraic effects. Because now I want get to be something that when code gives me back an S, and I want put to be something that when code with S just give me back a unit. So what would you put in the case of get? You need to return a free. So you first has to have an op, because it's not a value. And then what do you need? This is is the type you will get when you instantiate that f in the free monad two states, right? Yes?
Of pure,
Of a pure. Now you have an op. What do you need? You need a data constructor for state. So which constructor would you use? Get. And get takes one argument. What should I give it? What the argument would be? What would I want in this case? I want a function. So in this case, I want the whole result of this computation to be s, because I want to get s back if you call this get. Then, in that case, you would see that in the end, I want this a to be an s. Identity. Is identity good enough? Because in this case, I think this A is actually going to be this free, because the whole thing still needs to be wrapped inside that computation tree. Return. Okay, and similarly, what do I need in the case of put? I start with the op, and I need the put. And what does put take? Put takes the s. And then what would be this a? In this case, it's going to be again this free state a, because you need to get back to that computation tree. Right? Because you want the final result to be a unit. Like think about generic effects again. In this case, you want to give it an s and you want to get back a unit. And in the case of get, you want to give it a unit, but you want to get back this s. Okay, so now we got the wrapper functions for get and put. We can now define a program using stateful resources, using